When a scientist does an experiment, the data they collect helps them figure out whether or not the hypothesis they are testing is true. But how does that process work? How certain should we be that the experimental data support the hypothesis? And how do we know how much we should increase our belief in the truth of the hypothesis when the data support it? How data are used to provide evidence for or against a hypothesis is not at all simple, and is right at the heart of the reason why science relies so much on statistics. Scientists use probability and statistics to help quantify how the data they get from experiments or studies is evidence in favor of or against a hypothesis. But there is actually more than one way that statistics can be used to do this job. This video focuses on the debate between two fundamentally different approaches to statistical hypothesis testing. The first approach is called classical statistics because it is historically the most common approach. This approach involves comparing the hypothesis you are testing with the null hypothesis. The null hypothesis is the opposite of the hypothesis under investigation. It's the hypothesis that the phenomenon you're investigating in fact does not exist, and any differences in the data you get are just the result of random chance. Imagine doing an experiment to test whether a new flavor additive has any impact on blood sugar levels in mice. Your working hypothesis is that your additive will increase the mice's blood sugar levels. The null hypothesis is that the additive does not increase their blood sugar, so any difference in their blood sugar levels would just be the result of random chance. The hypothesis you're testing is that there is an influence between the independent and dependent variables in your experiment, the flavor additive and blood sugar level. The null hypothesis is that there is no influence between the two variables, and any correlation you might observe is purely coincidental. The null hypothesis entails a probability distribution of all the possible observed data you could get in your experiment. If there is no relationship between the additive and blood sugar, then it's most likely that a mouse that consumed the additive will have about the same blood sugar level as a mouse that has not. Of course, chance fluctuations and other sources of blood sugar differences mean that some mice will have higher or lower blood sugar. Average blood sugar level and how much variation is typical tells us what levels we should see if consuming the additive made no difference. If the additive makes no difference, that is, if the null hypothesis is true, it's very unlikely that lots of the mice in the experimental group have high blood sugar readings. This would be more and more unlikely the more mice are used in the experiment. This shows the importance of a large sample size in experimental design. Then, after we conduct the experiment, we compare our experimental data to our expectations from the null hypothesis. The probability of getting our experimental data, if the null hypothesis is true, is called the data set's p-value. Prior to the experiment, we should have selected a threshold for what p-values we will accept as constituted a statistically significant result. In many fields, the standard choice for a significance level is a p-value less than 0.05. If the p-value of our experimental data is lower than 0.05, this means that if the null hypothesis were true, there would be less than a 5% chance that we'd get this data. But we did get this data, so this experimental result is statistically significant and counts as evidence against the null hypothesis. Typically, we say that if the result is lower than the specified significance level, we reject the null hypothesis and instead accept the hypothesis we are studying, often called the alternative hypothesis. Imagine that in our experiment, mice in the experimental group who consumed the additive had an average blood sugar reading much higher than the average of mice in the control group. This would be very unlikely if the additive made no difference. If the average blood sugar reading in the experimental group is so high that the p-value is less than 0.05, then there is less than a 5% chance the null hypothesis is true, and we can reject the null hypothesis. Then we would conclude that the additive does increase blood sugar levels. This is called null hypothesis significance testing. This is by far the most common way that scientists quantify how the data they observe bears on the hypothesis they are testing. But there are a couple of strange features The first is that the probabilities under consideration are not the probability that the hypothesis we are studying is true, or even the probability of getting the experimental data according to the hypothesis you are testing. They are the probabilities that the data is true according to the null hypothesis. So, null hypothesis significance testing and other uses of classical statistics only indirectly bear on the hypothesis under investigation. The other main approach to using probability to quantify how evidence bears on hypotheses is called Bayesian statistics. It uses Bayes' theorem to calculate a conditional probability of how likely the hypothesis is given some dataset. So Bayesian statistics does try to give us the exact information we are interested in. Given the experimental data, how likely is it that the hypothesis is true? So, given the average blood sugar readings of mice who have consumed the additive, how likely is it that the additive increases blood sugar levels? But, just like with classical statistics though, there are puzzles. The major one is that Bayesian statistics needs to use a probability in its calculation that can be difficult or impossible to estimate. This is called the prior probability. The prior probability is how likely the hypothesis was to be true before we ran the experiment. In some cases, like if we already done some testing, we know enough to estimate the prior probability, but other times we don't. Some advocates of Bayesian statistics think that you can plug in any number for the prior probability because, as long as you run enough experiments, that number shouldn't matter. But this is a little troubling, since it means that two different scientists, both analyzing the same data, could come to different conclusions about how likely the hypothesis is. Statistics is a very powerful tool that scientists use to calculate the significance of their experimental results for the hypotheses they are testing. Interestingly though, there are two very different ways to use statistics for this job: classical statistics and Bayesian statistics. In some cases, one of these is a more natural fit than the other. The choice of which approach to use may come down to the kind of information you have available and what you're attempting to show. But interestingly, most scientists who use statistical methods are advocates of just one approach or the other, either classical statistics or Bayesian statistics. Bayesian statistics is becoming more and more common, but classical statistics is still, well, classic.